as we have had an idea on how differentiation works, and we can look at a couple of formulas that are there which are related to both integration and differentiation. So previously also I had given the formula, that is, if I have d by dx or d by dt of t to the power n will be nothing but n t to the power n minus 1. And on the other hand, if I've got integral t power n dt, then this can be written as t to the power n plus 1 by n plus 1. So these are the only two formulas that we will be using for the calculus that is there. And as and when needed, we will look at other formulas that are there. Now, we know that there are three equations of motion. The first one being v is equal to u plus at. The second one, s is equal to ut plus half at square. And the third one, v square is equal to u square plus 2as. Now all of these three we have derived graphically. So now let us go ahead and derive all these equations using integration and differentiation. That is the method of calculus that is there. So the first equation of motion is v is equal to u plus at. Now in order to arrive at this, we will take acceleration, which we have seen it as nothing but dv by dt. That is the rate of change of velocity. We will go ahead and do a small change. So dv is equal to a times dt. So similar to algebra, we cannot do it, but here algebraically what we are doing is we are making sure acceleration is time dependent. And now we will apply the formula of integration that is there. That is integral dv is equal to a dt. So I have another integral. So both the sides I have put my integration sign. Now before we proceed, a couple of things that we have to see. Here velocity and time we will have to define, because dv and dt are the values that are going to change. So we will have to define their limits. So when I tell define their limits, what is the meaning of that? That is, it's as simple as telling that when we are looking at the starting and the finishing point, what it is. So for instance, let us look at the time when it is 0. My velocity, I can simply write this as v is equal to the initial velocity. And when it is at a certain time t, the velocity is the final velocity. So we will have to apply our limits that are there. So dv varies with the limits from initial velocity to final velocity. At the same time, time varies from 0 to t. So this is how we usually write it. So t is equal to 0 to t is equal to t. Now let us go ahead and solve. If we see the first, let's say the LHS, integral dv is nothing but integral v to the power 0 dv. So the limits are from u to v. Now according to the formula that is there, t power n dt was t to the power n plus 1 by n plus 1. So here I can write it as v to the power 0 plus 1 by 0 plus 1. And this is how we are going to write the limits. So as soon as integration is performed, we are going to make sure that we put square brackets and we write the limits. As in any case, it has to be upper limit, that is the final velocity minus initial velocity, that is upper limit minus lower limit. So I have v varying from the initial to final. So we get this as v minus u. So this is our LHS. Let us look at our RHS. In the RHS, we have got integral a dt, where time is varying from 0 to some value t. And here if we see, acceleration is in a way independent of time. Though the formula is dv by dt, Here when we see a is not a function of t. So we can write it like this. So a is a constant. We take it outside the integral. Integral t is equal to 0 to t is equal to t dt. So what I will do again, just for simplicity's sake and for understanding, I'll put it as t power 0 dt. So this becomes a t to the power 0 plus 1 by 0 plus 1. T varies from 0 to t, which is equal to a times t, which varies from 0 to t, which is a t minus 0 is equal to a t. This is our RHS. So let us equate. LHS is equal to RHS. I will write my value, that is that the integral will start from there. Integral dv u to v is equal to a integral dt 0 to t. And the LHS we found it to be v minus u is equal to at, or v is equal to u plus at. So this is the first equation of motion that we have derived using the method of calculus. Now the second equation of motion that we have to arrive at is s is equal to ut plus half a t square. Now for this, what are we going to do? We have displacement and velocity as well as acceleration. So we can go ahead and take the expression v is equal to ds by dt, because this is the only way we will end up getting displacement. So on rearranging, I will get this as ds is equal to v dt, or ds is equal to u plus at times dt. Since we already derived the first equation, v is equal to u plus at. Now we can go ahead and put the integral sign. Integral ds is equal to integral u plus at dt, or we can write it in this particular way. Integral ds is equal to integral u dt plus integral at dt, or integral ds is equal to u times integral dt plus a times integral t dt. Now we have to look at the limits. So when time is equal to 0, initial displacement is 0. When time is equal to t, the displacement is written as s. So let us apply the limits. On application of limit, my expression will become s is equal to 0 to s is equal to s is equal to u times integral t is equal to 0 to t is equal to t dt plus a times integral t dt. T is equal to 0 to t equals t. Now since we have done the integration in the previous step, we can go ahead, or for the previous formula, we can go ahead and directly do it. So the LHS becomes s times, or we'll do it once more, s power 0 ds integral s is equal to 0 to s is equal to s, and now we'll go ahead and do this simultaneously so that we don't have to come back to this particular part again. So what I will do is I will just go ahead and write whatever new formula or new values that I'm going to put it in red. So s power 0 is not going to affect, you're going to get the same expression. This is t power 0 and this is t power 1. So our expression now, since we have written this, we can go ahead and integrate it. So this becomes integral s is equal to 0 to s is equal to s power 0 when we do. So without the integral, let's go ahead and solve it. We will get s power 0 plus 1 by 1, which I'm just writing it as s, varying from 0 to s, is equal to u times t, which is varying from 0 to t. Now here we have t power 1. So that we will get it as t to the power 1 plus 1 divided by 1 plus 1, varying from 0 to t. So this I will end up getting s minus 0 is equal to u times t minus 0 plus a times t square by 2 going from 0 to t. So I will get s is equal to ut plus, it was a t square minus 0 by 2, which we will end up getting s is equal to ut plus half a t square. So no other formula except for the one that we have seen. No geometrical confusion, straightforward substitution, the formula you apply and you arrive at the equation. So this is the second equation of motion. Now let us look at the third equation. The third equation is v square is equal to u square plus 2as. Now if we see s is there, so we will have to take the velocity expression only. But we also have acceleration. So how do we arrive at this particular form? So for that, we will have to take the following differential formula. That is, acceleration is equal to dv by dt. So in calculus, we can do certain algebraic, let's say, operations. So what I'm doing is I'm multiplying and dividing by ds. So this term, that is ds by dt, now becomes velocity. So here we can see that acceleration can be written as v dv by ds. Now if you see, v dv is there. So from the formula that we had done for t last time, we can see if it is t dt, we end up getting t square by 2. Now the similar thing we can do here. So what we will do, we will take ds to the other side. So a ds is equal to v dv. Now we have to set the limits for this. So integral a ds is equal to integral v dv, and here we can take the velocity is 0 for displacement 0, and for displacement which has a particular value, the velocity becomes v. Now instead of 0, what we will do is we will take this as the initial velocity. Ideally, when there is displacement is 0, body might not have any initial velocity. But in certain cases, it is seen that even though displacement is 0, it would have been moving previously with some velocity. So certain graphs give us that feeling. So right now we can go ahead and use these as our limit. Now a and ds, there is no dependence. So I'll take acceleration outside. Integral s is equal to 0 to s is equal to s ds is equal to integral v is equal to u to v is equal to v dv. So just like how I've done it previously, again I will just put in values here so that we can understand what the integration is all about. So in red, so this is s power 0, does not affect our equation. This is v power 1. So we end up getting a times integral of s, or integral of ds is nothing but s. So 0 to s is equal to, now integral of v dv is there. So I'll get it as v square by 2. So this is v square by 2 with the limit varying from u to v. So I will have a times s minus 0, upper minus lower limit, is equal to half is common. So it is going to be v square minus u square. So that would imply 2as is equal to v square minus u square, or v square is equal to u square plus 2as. And this is our third equation of motion that is there. So now let us look at the expressions that are given here. So I've got velocity time equation, distance time equation, velocity displacement equation. So the three equations of motion basically come under these three titles that are there. Now the first one is equal to V equals U plus AT is the velocity time equation. The distance time equation is the second equation, which is S is equal to UT plus half AT square. And the third one, velocity displacement equation, is V square is equal to U square plus 2AS. Now, among all three equations, we can work with the second equation in a way such that we can determine what is the distance traveled in a particular time. That is, we can derive a formula only to find the distance traveled in a particular time. Whereas in the other two cases, we will not be able to do it. So let us go ahead and derive that equation also. So let us use the second equation of motion in order to determine the distance traveled in a particular second. So I have got S is equal to UT plus half a t square. Now this is the equation that we have found, or we have derived, for when time t is equal to t seconds. Now let us take 1 second back, that is the previous second of this. So for instance, if we start from, let's say, t is equal to 0, t is equal to 1 second, and so on, we will have t as n minus 1 second, and then t is equal to n seconds. Or in other words, since we have already written it in terms of t, we can take this as t minus 1 and t seconds. So just 1 second previous to this, we are going to derive. So what we will do is t, we will write it as t minus 1. So the equation becomes S for t minus 1 will be nothing but u of t minus 1 plus half a of t minus 1 square. So let us take this as equation 1, and S at t seconds, we have already written it as ut plus half a t square. Now this is equation 2. So what we will do is, in order to calculate the distance that is traveled in the given time, we can simply write S is equal to St minus S of t minus 1. So that means S is going to be, St is what is written first, minus S of t minus 1, which ut plus half at square minus of u of t minus 1 plus half a of t minus 1 square. So that would mean ut plus half at square minus ut minus u plus half a. Now this is a minus b whole square. So I'll have t square plus 1 minus 2t. So I will get ut plus half a t square minus ut. So I'll multiply minus inside, and simultaneously I'll multiply half also inside. So minus ut, minus into minus, plus u, minus half a t square minus half a t. There's no t here, it's only 1 by 2a minus. So plus half a t. So a by 2 into 2t. So I will end up getting the following. So I can go ahead and reduce this. So half at square minus half at square I can cancel out, minus ut plus ut. So whatever I am getting, I will write it now as S is equal to U minus A by 2. So this is 2 and 2 will get cancelled, plus 18. So we have from this last equation, there is only U plus A by 2, or let's say if you don't cancel this, then we can actually do a little bit more simplification. So I will have, this would be A by 2 into 2t. So this we can write it as U minus A by 2 is there. Now we'll take that common. So when I take A by 2 common here, I will have, let's say, we'll put this as plus. Within bracket, if I'm taking A by 2 common, I will have minus 1 plus 2t of A by 2. So when I multiply it here, I'll get back this equation. Or I can rephrase and write this to be S is equal to U plus A by 2 times 2t minus 1. So this is the equation to calculate the displacement or the distance traveled in a particular time. So I can put my value of t here and correspondingly calculate the value of S. So now let us look at the idea of relative velocity. So when we are talking about relative velocity, what is it that we have to know? So when we talk about relative velocity, what are we trying to look at? Now let us assume that we've got two vehicles that are moving in these two directions. So I will take a block diagram for them. Let us see this as another vehicle. So let us take, let's say, a sports car that is there. So I've given a sleek design for a sports car and all of them are moving. So they are moving in a particular speed, and given that I label these as, let's say, A, B and C, I can talk about their velocity with respect to each other. What is the velocity of A with respect to? So WRT is the short form. Velocity of B with respect to velocity of C. Now the idea of doing this is, whenever we are on the road, we would have seen that a vehicle would overtake us, or we on the other hand can overtake a vehicle and come in front. So when I'm telling come in front, basically what happens, from behind we move and let's say this becomes our placement. That is there. So similarly, what happens, B can move and come ahead of A and so on and so forth. Now this can continue. Or we can have a completely different object or a different vehicle that is overtaking us, if we are not overtaking amongst ourselves. So here we can tell that one of them is moving slower with respect to the other. That means we are taking a reference point. Among these three vehicles, that is A, B, C, we are taking one of them as a reference, and with respect to them we are telling the others are moving fast or slow. Now this concept can be understood with the idea of vectors, or since we know a little bit about velocity, we can use the conditions that we have studied for velocity and apply it here to understand what exactly relative velocity is. So now let us go ahead and try and understand what is relative velocity in terms of, let's say, displacement along the x-axis and the velocity of these objects. So if I take VAB, it would be nothing but VB minus VA. So the difference in the velocity between B and A. So in order to keep things simple, let us look at only two objects instead of three. The same idea I can expand it to two and more objects. So we will keep velocity of A, displacement of A, displacement of B and velocity of B. So I've taken these two sets of, let's say, values that I'm going to look at. Now we know that velocity is nothing but displacement by time or distance traveled by time, which we take it as speed. Either one is going to work, so we will just use the formula that we have seen here. Now, displacement again will be done with respect to given time. So when t is equal to 0, xa will be equal to 0. So in order to keep things a little more, let's say, scientific, we will take when t is equal to 0 seconds, xa is equal to 0 meters, and when t is equal to, let's say, t seconds, xa can be written as xa of t meters. That means the idea here, because of writing this like this, xa of 0, xa of t means at time t is equal to 0, what is the distance? And at time t is equal to t, what is the distance? So if I have to write d, I would simply be writing it as, let's say for object A, if I'm taking d by t. So d can be written as x a of t, that is final, minus xa of 0. So substituting this expression here, I will get Va is equal to xa of t minus xa of 0 by t, or we can write this as xa of t is equal to xa of 0 plus Va times t. Similarly, I can do it for B. So xb of t is equal to xb of 0 plus Vb t. Now we can take these as two different objects and two different distances, or if I take, let's say, a path that is there. So I can take this as point A, this is point B. So whatever is the velocity measured at A, we can call it as Va, velocity measured at B as Vb. Similarly, the distances. Or we can consider it as two different objects. Either way, the understanding is one and the same. So if I take the difference between the values that are there here, let us see what we get. I will have xb of t minus xa of t is equal to xb of 0 minus xa of 0 plus Vb minus Va of t. So what I've done, I've just subtracted them. Now this equation is the one that is very crucial to us. So let me rewrite it. I have got xb of t minus xa of t is equal to xb of 0 minus xa of 0 plus Vb minus Va into t. So the distance at time t for 2 points or 2 objects is equal to the displacement or the distance between the 2 objects when time was 0 and the subtraction of the velocities. So this term here, Vb minus Va, is relative velocity. Now when I tell relative velocity, the question is with respect to what? Relative. That is, how fast, we can say again, how fast B is moving compared to A. So in this case, what we do is we go ahead and write how fast B is. So instead of moving compared to, we will just replace it with relative. That is, with respect to A, how fast B is moving. Similarly, if I go ahead and write the expression like this, let's say xa at time t minus xb at time t is equal to xa at time 0 minus xb at time 0 plus Va minus Vb of t Now this would mean that we are taking previously what we took, how fast B is moving with respect to A. Here we can take how fast A is moving with respect to B, or velocity of A relative to the velocity of B. Now these are for two objects. Or what is the velocity at point A relative to velocity at point B. Now with this in mind, let us go ahead and look at some cases that are there. So in the first case, we are going to tell the velocity is going to be the same. VA is equal to VB. So therefore, VA minus VB equal to 0, or VB minus VA is equal to 0. So either ways, since the velocities are the same, you're going to get 0. So what will the expression boil down to? So let's say if I take XB of t minus XA of t will be equal to XB of 0 minus XA of 0. So there is no velocity component at all. Now what is the meaning of this equation that is there? Now the understanding here, if you have to arrive at it, what we will do is we will do a slight change. I will take all the b terms together. XB of t minus XB of 0 is equal to XA of t minus XA of 0. So what I have done, I have just interchanged XA of t and XB of 0. Now the understanding that we can arrive from this equation is the following. That is, the distance that in between B and distance that in between A is a constant. So if we try to plot, let's say, the distance time graph for this particular case, or displacement time graph, anyways we can take it. X is in terms of meters, t in terms of second. This is how the graph would look. So this would be my first curve, or first line that is there. And as I told previously, geometry, every line can be called as a curve. So this is how it is. So I can take this for object A, this curve for object B. And you can see that they are equidistant. So since the velocity is the same, they are moving uniformly with respect to each other, or they are moving at a constant speed with respect to each other. Now let us look at the second case. So in the second case, I can take it as VA greater than VB. That would imply if I take VB minus VA, I will get a negative value. Or if I have VB greater than VA, since we had two different equations, the understanding would remain the same. VA minus VB, that means the negative value of velocity. Now, what is the meaning of this if you are going to plot a graph? Now here we are not going to substitute this in this equation, but we are just going to plot a graph and try and understand what it is trying to tell us. So in this case, what happens? I can have a graph which looks like this. And this is a, let's say, a real life case that is there, where you can get it like this. So what I am having here is, I have got two different slopes that are there for these, where A is having a positive slope. So if I take, let's say, the slope here, tan of theta, or B is having a negative slope. So A has a positive slope, B has a negative slope. Now that was what we saw, right? VA is greater than VB. Now here there's something which is lacking. Thing is, I have not labeled the axis. So what are we looking at? We will again be looking at a distance or displacement versus time graph. That is when we can arrive at velocity, right? So VA is greater than VB. So slope of A is positive, slope of B is negative. Or we can have it vice versa also. That time what will happen if I'm going to take, let's say, I'll write it in green color. So VB is greater than VA means the graph values will switch. This becomes B and this becomes A corresponding to this expression. So at that time what will happen? A will have a negative slope and B will have a positive slope that is there. So what is the understanding? If I take a point, the common point here, the understanding that we can arrive at this common point is one of them is overtaking the other, or one object is moving faster than the other. So at this common point, what happens? They overtake. So in this case, what is happening? A is greater than B, right? So A overtakes B. Whereas in the converse case, that is there. So I will draw the graph for that also. That is, if I have this graph and according to the green, if I label, so this was B and this was A, B will have a positive slope and A will have a negative slope. So VB is greater than VA. So what happens here? B overtakes A. It happens at a particular distance at a particular time. So if I take this to be, let's say, xt at x comma t. So for a given time at that particular distance. Similarly here, A overtakes B at x comma t. So for a given time and for a given displacement that is there. Now we can have another case also. In this case, we can take VA and VB of opposite signs. That means I can take VA is equal to minus VB, or let's say we can take instead of equal to, I can have a combination of VA minus VB minus VA and plus VB, which is very much possible depending on the direction that it is seen. Now, what is the understanding of this? Now, let us again go back to our expressions of two cars that are there. So, I've got two box cars, as we can call this. Now, they can be moving in two opposite directions. So, this, what I've drawn here as white behind, indicates the wind. So, let's say this is moving in VA. That means with respect to A, this is moving in minus VB, first case. Or for the second case, I can have my box car moving like this and the other one moving like this. So if this I'm going to take it as my direction of VB, then opposite to that is going to be minus VA. Both cases are equally probable. So if you understand one, the other also would manifest. Now, what is the understanding here? That is, if I have a person who is sitting in, let's say, the first car, he would see that the second car is moving faster than the car that he is in, he or she. Or if I have a person sitting in the second car, the person would feel the first car is moving faster. Now, this is a common feeling that we get when we look at trains. So, when we have two trains that are moving and we look around or we look out from one train to the other one, we do feel that the other train is moving faster than the train that we are sitting. So, how would the graph for this look? So, we can go ahead and draw it. And this is how the graph would look. So, let me first, without fail, label the axis. X is in terms of meters, time is in terms of seconds. So I will have my first, let's say, graph for the object would be something like this. So this I can take it as A. Since I've taken the case VA as positive and let's say VB as negative minus VB, I can have a slope, negative slope for B, something like this. So it can go on like this. So we will have one point here at a given time. We can see that in general it is not accelerating because these are moving in two different directions. That is the meaning of this symbols that I've written here. So it is not overtaking one and the other. What happens is they cross each other at that point without realizing who is moving fast. So for, let's say, if I take these two objects, so for this one, let's say for this fist that it is moving like this, the finger will see the fist as moving fast, or the fist will see the finger moving fast. So it would move like this. So in these cases, what happens? It becomes a little difficult to accurately determine which is fast, which is slow, if we are sitting in one of the vehicles. So if we have the case where the person is standing and observing the two cars that are there or the two trains that are there, which are moving in different directions, this person would be the right one to tell which one is moving faster with respect to the other because of the different directions. But otherwise also, person who's watching this will not be able to gauge because one of the cars is moving towards the person and one is moving away. So we need two people to actually observe, compare the time, compare the velocity or the distance that they have traveled in that particular vehicles, and then they can figure out. So now, this brings us to the end of this chapter. So as a recap, let us have a look at what all we have studied in this particular chapter, the formulas that are there, and then we will move on to the numericals. So let us look at the recap. We saw the difference between distance and displacement. That is both in terms of the symbol as well as what they actually do as scalars and vectors. We went ahead and calculated average velocity to be nothing but, let's say, v1 plus v2 plus v3 by 3, since I've taken 3, that is nothing but total displacement by total time. Now depends on which values are given. If we are given different velocities, we can calculate the average using the first formula, or we can calculate the average using total displacement and total time. Average speed in the same context, we would have found it to be nothing but the path length, that is the total distance that is there, divided by the total time. Next, we did go ahead and write velocity as nothing but the limit as delta t tends to 0. Delta, in this case, it was displacement, so we can write it as s itself. Delta s by delta t, or v came to be written as ds by dt. So we put an arrow on top to indicate that it is a vector. Similarly, acceleration was found to be nothing but limit delta t tends to 0, delta v by delta t, which was nothing but dv by dt. And acceleration, we found that we can write it even in terms of displacement in the calculus form as dv by dt, or d by dt of dv by dt, which is nothing but d square v by dt square. Then we did go ahead and calculate or derive graphically and using calculus the 2 or 3 equations of motion, that is v is equal to u plus at, s is equal to ut plus half at square, and v square is equal to u square plus 2as. Now the second equation we also saw that we can write the displacement or distance traveled in a particular time as s is equal to u plus a by 2 of 2t minus 1. Now the same equations of motion, when a is equal to g, we wrote it as v is equal to u plus gt, s is equal to ut plus half gt square, and v square is equal to u square plus 2gh. This is when the body is coming down towards the earth. When it is moving upwards away from the earth, there's only going to be a sign reversal. So v is equal to u minus gt, s is equal to ut minus half gt square, and v square is equal to u square minus 2gh. From here we went on to look at free fall, and we saw that in free fall u is going to be equal to 0 and acceleration due to gravity is going to be equal to the acceleration of the body, which is moving downwards. So our equations become v is equal to gt, s is equal to half gt square, v square is equal to 2gh. And finally we saw a relative velocity where the two bodies would move with respect to each other. VA B, which can be written as VA minus VB, and VBA, which can be written as VB minus VA. And we saw the various cases for this: when the object is moving at constant distance, when one object is overtaking the other, and the third case where the objects are moving in opposite direction such that the observer in one of the objects feels that the other is moving faster.